So hello everyone, and thank you for coming to my presentation. Today I would like to introduce the work that we've been doing at RWTH Aachen University at the Institute for Communication Technologies and Embedded Systems, which is entitled A Parallel SystemC Virtual Platform for Neuromorphic Architectures. Yeah, my name is Melvin Galicia, and currently I am a postdoctoral researcher at the ICE Institute and RWT Aachen University, and currently I am actively researching on neuromorphic computing systems. Okay, so let me get started with the motivation of our work. Basically, nowadays there is a need to explore new architectures because the von Neumann computational architecture that we've been using the last decade right now is performing poorly in applications for machine learning where a big data movement between the CPU and the memory is required. And here we spend a lot of energy and time to do that movement. Emerging technologies like ReRAM, resistive random access memory, have some advantages that can definitely help us to overcome that problem. The von Neumann bottleneck in this case is computing in memory. So neuromorphic computing is aiming to mimic the way our brain computes. All our neurons have the capacity to store information and compute over it. In this case, memory stores can emulate certainly the synapses in our neurons, and also when arranged in a cross-bar fashion or structure, they are very efficient to perform vector matrix multiplications, which are the main operations used in machine learning algorithms. So basically what we are trying to do here is use the same approach that's being used in the industry in the past for optimizing CMOS systems or exploring new architectures is by making use of simulators, virtual prototypes developed mainly in SystemC because it's very popular in the industry. Because they help you to do early software development or performance tuning or improvements in your architecture exploration, basically, without the need of having it like in physical, right? So we are trying to use this approach for neuromorphic systems, and what we did, we carry out a survey of what type of simulators are already being proposed in literature. And we found that many of them are quite simple and they lack accuracy, or some of them are very detailed, but they are quite slow because they demand a lot of resources to obtain such details. So some neuromorphic simulators are low level, so they help you to get good estimations of power, of performance, but when you try to scale them up in order to build, let's say, a full system that where you can really operate and execute artificial neural networks, the complexity becomes really high and the runtime becomes prohibitively, right? So basically what we did is trying to check what qualities in a simulators, like for example, architecture level, simulation level, circuit level, that where you can have exploration possibility, parallelization, and other qualities would be desirable in a simulator in order to fully exploit all the resources of the host system. Because imagine just without simulation, trying to run artificial neural networks models in a computer is already demanding, and try to run that in a simulator, that's what I said, that their runtime will become prohibitively slow. So we did our implementation of our virtual platform using SystemC, and you can see the high-level architecture of our simulator in this figure. We are using RISC-V, the open source CPU, and we want it to be as detailed as possible in a system level simulator. So we added data cache, instruction cache, buses, RAM memory, and of course the computing memory unit that we are using here as an accelerator. So when you zoom in into the computing memory unit, you will find all the necessary peripherals required to drive the crossbar, such as the digital to analog converters, analog to digital converters, output registers, input registers, and so on. When you zoom in into the crossbar, we will see that they are based on memory stores, and they can have different sizes. It's something that is configurable, but for this study specifically, we decided to make to give a specific value of 256 by 256, meaning that the biggest vector that you can multiply with a matrix is 256 by 256. As I said before, we implemented it using SystemC. So one of the things that we can take full advantage of is doing TLM transactions and tracing monitoring. In all these marks that you can see here, we are doing some tracing that will help you to quantify, to have a statistics of usage of your system while it is executing a given application. Meaning that you can, with that data, you can estimate, for example, the total number of accesses or read accesses, write accesses, for example, to the main memory of the or to the computer memory unit. And with that information, you could estimate, for example, the power required for the whole system for a given benchmark application. You can also estimate the full performance. You can check which unit is underperforming. And all the information that you can extract of the simulator during the execution of, let's say, an artificial neural network model. But SystemC also has constraint that it is a sequential language. It will not fully take advantage of your host system in that matter, because it will execute all the simulation in a sequential fashion, even though you might have a host core that has multiple cores. For that reason, we wanted to create a parallel SystemC virtual platform that will allow the exploitation of all the resources in the host system. The idea here is that we will have a SystemC controller that will act as the main simulation. And then we will have segments, which each segment represents a thread on your host system, meaning that those threads are just limited by the numbers of cores in your host system. You can instantiate as many as your host system will allow you. So the SystemC controller will act as the main simulation, and those segments can simulate independently of other segments because they have their own SystemC kernel. But because the virtual platform needs to have, depending on how you segment your virtual platform, there must be a need of communication, synchronization between them, and that's the communication mechanism that is implemented, which has a very important role on synchronization events within the virtual platform and synchronization events for the SystemC controller. Here, the SystemC controller will be in charge of stepping time on simulation and enforcing synchronization of all the segments. And additionally, when using the time decoupling technique, which basically is relaxing that synchronization, you allow certain segments to run ahead of others to gain time. And that's why, because now every single segment has their own time, we need to assign some time latency in each of the segments. And that's the work of the SystemC controller to monitor those time latencies. Let it see more clear here in this example. For example, if we run it sequentially, the controller will have to initiate the execution of one of the segments, let it run for any instruction, and then synchronize. When that synchronization happens, the next segment will happen, and after it finishes instruction, it will synchronize, and then the controller will do a time step of the whole simulation. But then if we run it in a parallel fashion, the controller will allow the execution of in parallel of each segment, and then when they are done, they will do the synchronization. But because we are using time decoupling, it can happen that one segment will finish much faster than the other because it doesn't need to run as many or any instructions, but other segment has to. So the time decoupling technique consists in allowing one of the segments to go ahead on time until certain time latency is exceeded, and then the controller will stop it and enforce the synchronization. All right, let me try to explain previous concepts into a more graphical way with one of the architectures that we were exploring. So if you recall the virtual platform that I was introducing in previous slides, what we've done is breaking it down into small pieces and assign those pieces to a different segments. And if you see here, segment 0 now has a RISC-V CPU and its corresponding computing memory units. Segment 1 has another RISC-V and its corresponding computing memory units. So now we brought our virtual platform into a multi-core system. And in order to continue instantiating more cores, we just need to instantiate more segments and create new channels within those segments. So, and that is a very easy way of making the whole system multi-core. As I previously mentioned, now each segment is an individual host machine thread. What we've done after that is running benchmarks in a sequential and a parallel fashion. Those benchmarks, for instance, are mobile nets for a convolution layer that has different parameters, M and MP of the artificial neural network, and a different mobile net for a different convolutional number of layers. We did that for ImageNet and for GoogleNet. And what we found is that, of course, it was expected, right, that while running the very same benchmark in a parallel fashion, we had some speed up compared to run it into a sequential simulation. Speed up of 2x, 2.3x depending. Each speed up depends on the workload you're running, the time decoupling that's happening, and the number of segments that you declared for that specific run. So that's the architecture that we call uniform segmentation. Now I will explain the one that we call load-oriented segmentation, because we have this parallelization way of doing it by segments. We can divide the whole virtual platform in different ways. Take a look here. Now we have segment 0 that only contains the CPU and the shared memory. This CPU can be used to run a different type of benchmark, while one RISC-V one, which is in charge here, in this case, he's in charge to orchestrate the whole, all the computer in memory units. That's the way we did it for this specific architecture. So you can have different loads and different type of segmentation of your virtual platform. And then the speed up will depend on those type of segmentations and breakdown of the virtual platform that is done. So as you can see, we run again the very same benchmarks, but for a different segmentation technique. So now we have 3 segments. Segment 2 is just running computing memory units, and similar as segment 3. So what you can see here is that again we got a speed up compared of 3.4x compared to its sequential counterpart. But here something is not so easy to observe, but for example, now we have 4 segments, we don't have a 4x speed up. Why? Because when we analyze the instructions that we're executing inside our virtual platform, we found out that segment 0, this CPU is not doing much. We could have assigned another type of load, but he's not doing much. So accelerating segment 0 does not really improve the main workload that is happening between work 1 and to segment 1 to segment 3. And that is something that needs to be taken into consideration when breaking down the virtual platform. All right, let me summarize this presentation. As conclusions, I can say that this work presented a parallel SystemC virtual platform that helps to fully exploit all the resources available to the host system machine while running simulations for the integration of neuromorphic accelerators within multicore systems. Also, this work shows that using parallel SystemC is a very effective methodology for the exploration of neuromorphic architectures. Experimentation using our virtual platform shows that the speed up time is directly related to the number of segments instantiated within the virtual platform, the number of cores available to the host systems, and the type of workload segmentation done inside the virtual platform. An outlook for our work is that we would like to continue our efforts for achieving a semi-automatic or full automatic load segmentation, because this will be a very nice starting point for designers when they have some knowledge of the type of workload that the virtual platform will be executing. Thank you very much for your attention. If you have any questions, I'll be very happy to answer them. Anyway, you can always contact me directly through email and I will be replying there. Thank you.